everyone, this is K Devender Reddy, Assistant Professor in Department of Electrical and Electronics Engineering. In this video, we are going to discuss about EMF equation of an alternator and the winding factors of an alternator. So consider the following. Flux per pole in Webers, phi equal to flux per pole in Webers. P is the number of poles. Ns is the synchronous speed in terms of RPM, rotations per minute. F is the frequency of induced EMF in hertz. Z is equal to total number of conductors, stator conductors. Z phase, total number of conductors per phase connected in series. T phase, number of turns per phase. Consider, in this case, consider a concentrated winding and a singleton coil. Consider a single conductor placed in a slot, one conductor in a slot, and considering by assuming it as a concentrated winding, I am derived the expression for EMF. Later we will discuss the effect of distributed winding as well as the short pitched winding. Average value of induced EMF in a conductor is equal to ratio of flux cutting in one revolution by time taken for one rotation. Average value of induced EMF in a conductor is equal to d phi by dt. Time total flux cut in one revolution is equal to phi p. Time taken for one revolution is equal to 60 by ns seconds. Average EMF induced in a conductor, that is d phi by dt, is equal to phi p by 60 ns. This is phi p ns by 60, and we know ns equal to 120 f by p, so f equal to p ns by 120. So we have p ns by 60, that is 2 times of pi into f. 2 times of pi into f, that is the induced EMF, that is called the average value of induced EMF, is equal to 2 pi f. If there are z number of conductors are connected in series per phase, then average value of induced EMF is equal to 2 pi f z. Now we know number of conductors z is equal to 2 times of the number of turns. So average value of induced EMF per phase is equal to 2 pi f t into 2, that is 4 pi f t volts. And this is the equation we have, and by considering the form factor, the average value of induced EMF is equal to 1.11 times of 4 into pi into ft, which is equal to 4.44 times of pi ft is the average value of induced EMF in terms of the volts. But this equation is not valid if the winding is distributed and if the winding is short pitched. This is the equation valid only if the winding is concentrated and if the winding is full pitched. But there is a case most of the alternators use short pitched winding over the full pitched winding, and we can also use a distributed type of the winding. In certain cases, in such cases, this EMF equation is not valid. We have to consider the winding effect, that is called a pitch factor, as well as the distribution factor of the alternator. So winding factor is a product of pitch factor as well as the distribution factor, Kp and Kd. First we have to derive the expression for pitch factor. Later we have to derive the expression for distribution factor. In short pitched coil, the induced EMF of the two coil sides get vectorically added, and that will gives you a resultant induced EMF. But in the case of the full pitched winding, the induced EMF of the coil sides will be arithmetic addition. So obviously the arithmetic addition of the induced EMF is higher than the vectorical addition of the induced EMF. So in a short pitched winding, especially, induced EMF may get affected by the short pitched winding, but the sinusoidal waveform, the output of the sine wave will be more clear sine wave will having the output voltage. Let us assume coil is short pitched by an angle alpha. The EMF induced per coil side is E. When the winding is full pitched, the arithmetic sum of the induced EMFs are 2E. Two sides we have each side E, that is E plus E, that is 2E induced EMF of the alternator windings when the armature is full pitched. When the armature is short pitched by an angle called alpha, the induced EMF is vectorically added, that is ER, resultant induced EMF, equal to 2E times of cos alpha by 2. Let us now define, we know the definition for pitch factor. Kp is equal to resultant induced EMF of short pitched coil to resultant induced EMF of full pitched coil. So short pitched coil means it is vectorically added, and it is arithmetic addition. Full pitched winding is arithmetic addition and short pitched winding is vectorical addition. So Kp is equal to 2E cos alpha by 2 by 2E. These two are cancelled. Pitch factor is equal to cos alpha by 2 is the expression for coil pitch factor or coil span factor of the alternator when it is a short pitch angle. And in the case when the harmonic content will come into the picture, the Kp also affected by the harmonic content. So here I am naming as order of the harmonics are R. So due to the harmonic content, the output waveform will not be much smoother waveform, will not get it from the alternator. So if there are R order of the harmonics will come into the picture, so KPR, the pitch factor for rth harmonic, is equal to cos R alpha by 2, where R represents the order of the harmonics. Similarly, the distribution factor, if all the coil sides of any one phase under one pole are bunched in one slot, the winding obtained is known as concentrated. That we know, the concentrated winding, in the case of the concentrated winding, number of slots are equal to number of poles, and entire winding of the armature is bunched in a one slot or bunched in under one pole influence, then that kind of winding is called a concentrated winding. But whereas in the case of the distributed winding, the armature winding, a number of slots are not related to the number of poles. The armature winding is distributed over the armature slots. The stator armature slots, the entire winding will be distributed uniformly over the stator, that is over the armature slots. So in such case, the induced EMF may get affected in the distributed winding because the flux density is different. When we go away from the center of the pole, your flux density is decreasing. Obviously, we know the induced EMF is directly proportional to the flux, though it is proportional to the density as well. So if the distributed winding case, in the case, the flux density will decreases when we go away from the center of the pole, even though the output waveform will be more smoother than the concentrated winding, but the quantity of induced EMF may get affected, but the resultant output will be a more smooth sinusoidal waveform will come into the picture. So let us define the proper definition for a distribution factor, which is the ratio of induced EMF in a distributed winding by induced EMF if the winding is concentrated. Let us take it as per phase quantity. There are AC coil, CD, DE, EF, up to F we have EF, and beta is a slot angle, M beta by 2. This is my, for each of the coil, draw the bisectors, and the angle between these will be beta by 2, and this is a beta for each of the coil, and the total number of coils are M. So the total slot angle, the phase angle is M beta. Now, a pitch factor, when we talking about the distribution factor, let us talk about N is equal to number of slots per pole, and M equal to number of slots per pole per phase. Number of slots per pole per phase, and EC is the induced EMF per side, per coil side, and beta is the angular displacement, that is equal to 180 degree by N, that is number of slots per pole. Number of slots per pole. Now let us represent the EMFs induced in the different coils of one phase under one pole. AC is a one coil, DC, DE, EF, and so on. There are so many coils are there. They are equal in magnitude, but they are differ from each other by an angle called beta. If you draw a bisectors for each of these coils, they would meet at a common point O, and EMF induced in each coil is equal to 2 OA sine beta by 2. As a slot per pole per phase is M, the total arithmetic sum of all the induced EMF per coil side per phase is equal to M times of 2 OA sine beta by 2. Now we have a resultant induced EMF would be represented AB, that is ER is equal to, or the phase EB is equal to 2 OA sine of angle between AOB by 2, that is 2 times of OA sine M beta by 2. Now we know the KD is equal to the phasor sum of components, that is the resultant induced EMF when it is a distributed winding, that is 2 OA sine M beta by 2 by induced EMF, that is arithmetic induced EMF, that when the winding is concentrated, that is M into 2 into OA sine beta by 2. These 2 OA cancel each other, and KD equal to sine M beta by 2 by M sine beta by 2. This is the expression for distribution factor of the alternator when the winding is distributed. Similarly, the order of the harmonic can be represented by R. So distribution factor KDR for the order of the harmonic is equal to sine M R beta by 2 by M sine R beta by 2. This is the expression for distribution factor. So this is the case. The winding factor is equal to Kp and product of Kp and Kd. Now we can write down the expression for induced EMF is equal to 4.44 times of pi into F into turns per phase into Kp and Kd. And this is the expression one. It is valid for both the kind of windings, that is a concentrated, short pitched, and distributed winding. This E is equal to 4.44 times of pi into F into T. Expression number 2, it is valid only if winding is full pitched and concentrated. If the winding is full pitched and concentrated, then only the equation number 2 is valid, and the equation number 1 is valid for any type of the winding structure. And Kc is equal to 1 when winding is full pitched, and Kd is equal to 1 if winding is distributed, if winding is concentrated, and Kd and Kc both are less than 1 if the winding is short pitched and if the winding is distributed winding. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.